I'm a logic answer.
All right. So thank you for coming back to the lecture. What I want to do this class is sort of, mostly the boring stuff. I want to lay out the basic notation and define the basic objects that we're going to be manipulating throughout the semester, so that we can do more interesting stuff later. So, in general, we're going to be thinking about prediction tasks. That are defined over some labeled domain of labeled examples, which I'll generally write, I'll try to write some kind of fancy looking Z for the domain. So this is really the Cartesian product of feature space, which is written as a fancy looking X, together with a labeled space, which is a fancy looking Y. Pretend the Y is a little fancier looking. So here, I'm leaving this abstract for now because in different applications it'll be different. But X in general represents the space of features you observe before making some prediction. So they could be binary if it's, the features are yes, no kinds of things. They could be real valued or whatever. Similarly, Y is an abstract label space. This is the kind of thing you're trying to predict something about. It could be a regression setting. So for example, it could be that Y is some d-dimensional real value space, right? Maybe we're trying to predict something like, expectations of Y. Or if we're in a classification setting, it could be that Y is some discrete set. Maybe it's labels of an image, and maybe there's 1,000 labels. It could be a bicycle or a hot dog or a cat or something like that. Okay, so at this level, like Y could be anything. Oftentimes, though, especially at the beginning of the class, we're going to think about like the one-dimensional regression kind of problem, in which case you should think of Y as just being like real values. The labels are going to be numbers, say, between 0 and 1. Okay, now there's going to be two main learning settings that we study in this class, sort of the batch or distributional setting, which is maybe the setting you're most familiar with if you've taken like a regular machine learning class. That's the setting in which there's some distribution over data. You'd like to learn something about that distribution. You don't have direct access to it, but maybe you've got a data set which is sampled IID from that distribution. We'll spend about half the class thinking about that setting. Another setting we'll think about that maybe you've had a little less exposure to unless you've taken a more specialized class is like a sequential learning setting where there might not be any data distribution. What happens is that examples arrive one at a time according to some arbitrary process, at which point you need to make a prediction. Only after which will you observe the true label, and then this process continues. Okay, but I want to define things in a way that'll sort of make sense in both of these settings right now. Okay, so if we're in the distributional setting, then there'll be a distribution. So the notation I will use for that, for an underlying distribution, is fancy D. This is an object that is a distribution over the data domain. Okay, so just to maybe explain some notation that I'll be using quite frequently. If I've got some set of elements like fancy Z, and I write this triangle in front of it, which maybe you can read as the simplex over. This is the space of probability distributions over that set. So if I have a distribution fancy D that is in the simplex over the data domain, that's just some distribution over feature label pairs. Okay. And we'll be interested in different parts of this distribution, right? So this is some distribution over feature label pairs. The features are the things that we get before we make our prediction. We're trying to make predictions about the labels. So it'll sometimes be helpful to write D sub fancy X. This is a distribution over just the features. And this is the marginal distribution for features over X induced by the full distribution. Okay, so what is this marginal distribution over the features? If you want to sample from it, you just sample an XY pair from the data distribution and you throw away the Y. Okay, so I've got this distribution over feature label pairs, but if I don't want to, I don't need to look at the labels. I can just look at the features. That's the distribution over those features is this thing I'm calling D sub X. It's just the induced marginal distribution over the features. Okay. It'll also be helpful to think about, so here we're isolating the distribution over the features. It'll also be helpful to sometimes isolate the distribution over the labels. But generally, I'm not going to be interested in the marginal distribution over the labels, like what I get by throwing away the features. What I'm going to be interested in is the conditional distribution on the labels, the distribution on the labels that I get for a particular X. This is somehow the object that I'm generally ultimately trying to learn, the conditional distribution on the labels given the features. Okay, and so the notation that I'll use for that is D sub fancy Y of X. Okay. It takes an argument. It takes a feature vector as an argument. This thing is distribution over the label space, and it is conditional distribution on the labels given X. Okay, so this is one of those, this is sort of the distribution over these kinds of individual probabilities we were talking about last class, right? Like if the X's are in a weather prediction scenario, the set of features that we collect from our weather balloons and our radar and our satellites and whatnot, D sub Y of X is like, because the probability that it will rain today, given X. Okay, so this thing is what we, in general, ultimately want to learn something about. Like maybe we want to know the expectation of that thing if we're trying to figure out the probability it's going to rain, or maybe something else. And, like we'd be really happy if we could get our hands on this object, but this is the kind of object that we sort of argued informally last time is going to be hard to get our hands on. And so that's what we're going to spend a lot of this class thinking about, how we can do useful stuff even without getting our hands directly on this object. Okay, so like, an idealized goal, so say we're in a setting where what we care about is the label expectation, the probability it will rain, or the probability that Alice will die in the next 12 months, or the average number of inches of rain, okay, some regression scenario. Like our sort of, idealized goal would be to learn F star of X, functional call F star of X, which is maybe just defined as the label expectation when the label is sampled from the conditional distribution on labels given X. Okay, like this, if we could learn this object, these would be sort of, this would be the thing that would get our hands on like the actual unknowable individual probabilities we talked about last time. This would be really the probability that it rains today. Okay, so that's sort of, we're not going to be able to do that, but that's the kind of thing we want to do. Okay, and so, yeah, so we're not going to come up with f star of x generally. We're going to come up with some other function f of x that maps features, say, to labels or to numbers if we're interested in the expected label. And okay, you know, like we're going to need some way to evaluate how well we've done. And through a lot of this class, we're going to be thinking about more fine-grained metrics in which we can do that evaluation. But maybe like the first thing you would think of having taken, you know, like a machine learning 101 class is we should just measure the error of our model according to some loss function. How good is it at predicting the labels? And a loss function that's going to be important for us for reasons that we'll see and give you today is squared error, which is also sometimes called the Breyer score. So once we have a distribution and we've learned some predictor for the label in a regression setting, so this is all in the one-dimensional regression setting. Squared error. I'll tell you that this is also known as the Breyer score, because I'm going to otherwise confusingly use the word B to represent it, use the letter B to represent it. Of a predictor to some function mapping features to real numbers on a distribution D is just, all right, B of F D, B, the Breyer score. It's just the expectation over labeled examples drawn from this distribution of the difference, the squared difference between the predicted label given our model and the real label. Okay. So, you know, like you've probably encountered this before, like if you're doing something like solving a linear regression problem, you would take f to be some parameterized linear function of the features, and you would explicitly like just solve in closed form for the parameters that minimize squared error. Okay, or if you use this as an objective in your neural network, this is a very standard loss function. And what we'll see, you know, like we'll see this in a bit. You know, you might wonder, like the first time you took a statistics class or something, why linear regression, say, is defined as minimizing squared error instead of some other loss, right? Like you could imagine minimizing some other loss. You could minimize absolute loss. You could minimize, I don't know, like error to the fourth. Why is it minimize squared error? Does anyone like know what nice properties squared error has?
Because it minimizes the conditional mean.
Yeah. Good. So we'll prove this in a moment. It's pretty straightforward. But the property of squared error that's going to be useful for us when what we're trying to do is learn functions that are good approximations of the conditional label expectation in various ways is that squared error has the property that it elicits the mean. Okay, so if I have a distribution and I want to figure out what is the mean of that distribution, and you know, my set of models is say just constants, right? Going to compute the mean of a distribution, I could just take a bunch of samples and average them. Or I could do the seemingly more complicated thing of minimizing squared error over all constant models. But minimizing squared error over all constant models would recover for me the mean of the distribution. That's not true of all other loss functions. Okay, so minimizing squared error is is a good property for if what you're interested in is expectations. And again, we'll see this in a moment as a corollary of a simple lemma, but amongst all possible models, f star of x, the thing that predicts the true conditional mean, conditional on x, has the minimal possible squared error. Okay, so like if you could somehow optimize over all possible models without any kinds of data or computational constraints, minimizing squared error would recover this idealized object. Okay, that's not true of all loss functions, and that's one thing that makes squared error special. I mean, it's not the only thing that elicits the mean, but it is like the important property we're going to use. Okay, does that make sense? Okay. Oh, but like think of squared error as closely tied to the mean. This, one of the things we're going to do in this class is to think about approximating expectations, but that's not the only thing. We're going to think about approximating other properties of distributions as well. When we need to think about other properties of distributions, we're going to use other loss functions that elicit those. Okay. So, squared error, the way I've defined it, it's parameterized by the distribution that I care about, and it's an expectation over that distribution. But one difficulty in machine learning, of course, is that you don't have direct access to the distribution. In general, what you have is a sample of data, right? I might have, 1,000 points, that are ideally sampled from the distribution, but I have to basically do everything using my data sample as a proxy for the distribution, and hopefully we'll be able to connect performance on the finite sample we have to performance on the underlying distribution. So in the batch setting, we'll generally have a sample, and we'll write D, which is supposed to be less fancy than this D. If it's a fancy D, then it's a distribution. If it's a less fancy D, it's a sample. For a sample, we have endpoints in this data domain, so labeled examples. Quickly sampled IID from the distribution. And oftentimes we'll treat a sample as if it's the distribution. So we might do things like minimize, find a model that minimizes squared error over the sample, for example. Just to make that notationally easy, I'm going to sometimes associate a sample with the corresponding empirical distribution over that sample. Okay, so a sample is just, like n points. The empirical distribution on that sample is just the uniform distribution over that n points. And in general, so I don't need to have separate notation for everything. I will allow myself, whenever I have some function that's defined over distributions, like the Breyer score, I'll allow myself to place as an argument to that a sample, and I will always interpret that just as the empirical distribution over the sample. Okay, so for example, if I were to write, the Breyer score of a model F on a sample D, well, it would be this expectation of the empirical distribution. What's the empirical distribution? It's just the distribution that places weight 1 over n on each of the samples. So this expectation would just evaluate to the empirical average squared error. So the average over all of the data points in the sample of the squared error of the model evaluated on that data point. And this is just the expected error over the distribution that is the empirical distribution on this sample. Okay, so in general, notationally at least, I'll treat data sets as if they were distributions. Of course, we will need to at some point prove theorems connecting performance metrics that we can achieve on samples to those same metrics on the distributions from which they were drawn. Okay, makes sense. Okay. Okay, so this is sort of the notation and background for the sequential setting. The sequential setting, sorry, this is the notation and background for the batch setting. The batch setting is sort of the standard setting in machine learning, right? Like this is sort of like a standard thing you do, like in your first machine learning class, there's a distribution, you've got like a training set, maybe you evaluate things on test set. You really hope that these things are drawn from the same distribution. In lots of scenarios, of course, like that assumption will be broken. Things change over time. And so we're also going to study a sequential prediction setting that is sort of the polar opposite of the batch setting in terms of how well behaved things are. You can, of course, imagine things in between. But in the batch setting, you sort of imagine every single data point is sort of exchangeable with any other. They're all the same. They're all distributed in the same way. The future is like the past. And so there's something you can hope to learn about the underlying process, D, fancy D, the distribution from which the data is sampled. In the sort of sequential adversarial setting, there's not going to be any distribution at all. And so it doesn't even make sense to talk about like a training set. There's no like train test split, like sort of prediction will be interleaved with data gathering in the sequential setting. Okay, well, what's going to happen in the sequential setting is that we will interact with some arbitrary process, which I will call an adversary, in rounds. Okay, so the learner will interact the adversary in discrete rounds, which I'll index by little t and will range from 1 to capital T. And what's going to happen in this interaction? Well, at each round, little t, the adversary chooses potentially using randomness, a distribution over feature vectors X and labels. Eventually, when we sort of analyze this, analyze these kinds of scenarios as games, we'll sort of see that there's actually no reason for the adversary to randomize the feature vectors, but they may well have good reason to randomize the labels. Okay, so at round 1, the adversary, like using information that they have from previous rounds of the interaction, like commits to some distribution on feature vectors and labels. And shows the feature vector to the learner, but not the label. Okay, so a realized feature vector xt shown to the learner. Okay, then having seen the feature vector, the learner will make some prediction. They'll commit to some prediction. Okay, I'll be sort of coy about what the form of that prediction is for now, because we'll be thinking about predictions of different types. But the learner makes some prediction. See, the prediction could be a number. It could be trying to predict what it asserts is like the expectation of the label, like what's the probability it's going to rain. It could be a prediction set. It could be predicting a quantile. It could be any number of things. But in this general framework, the adversary shows the learner a feature vector. Then the feature vector then the learner makes a prediction. And finally, the adversary reveals the label. And this goes on for t rounds. And so these triples, the feature vectors, the predictions, and the labels, they accumulate into some transcript of length t. Okay, so this interaction accumulates with transcript I'll call pi t. And it's just the sort of recording of everything that happened in the interaction, which in this case is just at every round, there was a triple, feature vectors, predictions, like. Just to give some color as to what's going on here, the adversary is going to be a pretty powerful object, or sort of said another way, we're going to make very few assumptions about the adversary. So the adversary could really be some arbitrary randomized mapping from the past, from prefixes of the transcript that have been realized so far, to arbitrary distributions on feature labeled pairs at the next round. Okay, so we're not going to assume anything at all that, like we're not going to assume that the adversary is just like drawing examples IID from some distribution, or even that they're following some more complicated but still like well-specified like statistical process. The adversary could be a completely arbitrary adaptive algorithm mapping history to their choices at this round. Okay. Okay, so the adversary is quite general. We're making like no assumptions at all about them. That's why we're calling them the adversary. And we're going to ask for something. Oh, but like, what is our goal in such a setting, right? Like, in the batch setting, our goal ultimately is to like learn something about the underlying distribution. Like our stretch goal here was to really learn this function f star, which maps x to the expected label conditional on x. But in this like sequential setting that I've written down here, there is no underlying distribution. There's no underlying process. So what is the thing that we hope to do? Well, there'll be various things we hope to do, but basically anything we want to do in the batch setting, that we want to sort of learn about the distribution, we're going to want to do the same thing in the adversarial setting, where what we're going to mean by the distribution is the empirical distribution on the transcript that is realized ex post, that's realized after the fact. Okay, so for example, like there will be many examples of this, but like, for example, just to draw the analogy with squared error, the one thing we've defined so far, we could ask what the squared error of the learner in the sequential prediction setting is. Here again, I could write the Breyer score. Now there's there is no distribution, and there's no like model even, like the predictions are made in this process. So the Breyer score, the squared error would just be a function of the transcript. The predictions are sort of interleaved with the outcomes. In fact, the outcomes at later rounds can depend on the earlier predictions, because the adversary is allowed to make adaptive choices as a function of what the learner has done earlier. But still, like the squared error is, a well-defined thing. It's just the average over all of the rounds of the transcript of the square difference between the prediction made at round t and the outcome realized at round t. Okay. So in general, like one thing we'll try to do in this class is whenever we show we can do something, whenever we prove some theorem in the batch setting, we're also going to try to do it in the online adversarial setting. Doing it is generally going to be like well-defined. It'll just mean accomplishing the same thing we did in the batch setting over the underlying distribution, but like ex post on the empirical distribution defined by this transcript. And this is going to be something that seems, on its face at least, much more ambitious, because we're going to demand algorithms that have guarantees simultaneously for all possible adversaries. Okay, so like when we ask, we haven't defined calibration yet, except informally last class, but like, for example, in the batch setting, if I just asked you to make calibrated forecasts, it would be like, maybe since you don't remember the definition of calibration, you'd have to like think for a minute, but like it wouldn't take you very long to figure out how to do that, right? Like one very simple way to make calibrated forecasts is just to predict the mean, the distribution, right? It's not like, it wouldn't be like a terribly compelling weatherman, but like it would be a calibrated weatherman if you figured out like what was the long run frequency of rain in Pennsylvania. And maybe it rains on 15% of days, and every day you just woke up, you got on TV, and you said there's a 15% chance of rain. Okay, that would be a calibrated forecast, not a very good one, but it would be pretty straightforward how to do that. You'd take some samples, you'd average them, and you'd figure out what was the expected frequency of rain in Pennsylvania. And because we believe that weather, at least over long time scales, the physics of it might be complicated, but we have things like the law of large numbers. It converges to some sort of predictable statistical process. We'd sort of expect that the frequency of rain, we could learn it from past data, and it would continue to be correct in the future. Right, so there'd be a straightforward way to be calibrated. But if you think about it, like and so this is, by the way, like foreshadowing one of the reasons why regular old calibration isn't a very useful guarantee on its own in the batch setting, and we're going to think about how to strengthen it. But even this very minimal requirement of like regular old marginal calibration, it's like not obvious how to accomplish it in the online adversarial setting, right? Because the premise of this dumb strategy for like the lazy weatherman who was just going to like predict the mean every day was that there was this thing called the mean, right? That was like a property of the underlying distribution, that there was this thing you could learn, mean of the distribution. And because data was sampled IID from this distribution, like this thing you'd learned from the past would continue to be the mean of the statistical process in the future. But of course, here, there is no statistical process. There's no mean you could learn. There's no particular reason to think that for the adversary you're facing today, the frequency of rain in the past will have anything to do with the frequency of rain in the future. And so even attempting this like, sort of like clearly only like marginally useful prediction methodology that is exploiting the weaknesses of the calibration definition, even attempting this thing of just predicting the mean every day, like it doesn't even make sense in the online adversarial setting. So even if I just ask for online, even if I just ask for marginal calibration, it's not at all clear how to do it. And one of the things we will see in this course, and for those of you who've seen it before, like maybe you've become jaded to it, but I'm hoping that there are enough of you who haven't that you'll be able to appreciate it, and I'll be able to appreciate it secondhand through your wonder and awe, is that absolutely everything, essentially, that is possible in the batch setting is also possible in the online adversarial setting somehow. Okay, so keep your eyes open for that. Okay, cool. So this was all just notation, but does it make sense? Questions about it? If there are notational questions, this is a good time to ask them, because otherwise it's going to get confusing real quick. Yeah.
In the sequential setting, do we fix a set of distributions over which the adversary chooses, or not even that?
No. I mean, we could. You could define a restricted setting where the adversary has to choose, distributions that aren't too concentrated anywhere. But in general, no. Like in general, the adversary is free to choose whatever they want. So it's a very challenging seeming environment to work in. People do study restrictions along the lines that you're talking about. So there are some that like, yeah, I was a little too glib when I said anything you can do in the batch setting, you can do in the online adversarial setting. There are things you can't. And people sometimes try to like fix that by saying, okay, the adversary isn't allowed to pick from arbitrary distributions, but they have to pick from distributions that are sort of sufficiently noisy, right? So maybe you sort of imagine that the adversary, maybe there's measurement error or the adversary has a shaky hand or something. So like one thing people study is they say, and maybe the adversary can pick, and this makes more sense in real valued settings, but they say maybe the adversary can pick an arbitrary point X, but then like what's going to happen is before it's shown to the learner, maybe Gaussian noise will be added to each board or something. So just to make sure it's not too fixed. The adversary still has a lot of power, but not on the low order bits. This is sometimes called sort of a smoothed adversary. And sometimes you can do stuff in settings like that sort of are, mild, correspond to putting mild constraints on the adversary. But the way we're mostly going to use it, no constraints at all. Good question. Yes.
Is the distribution in sequential setting generally static?
What do you mean the distribution in the sequential setting?
Like is the adversary allowed to like choose different, like say like for first T steps he like samples access from one distribution and then he's allowed to like have a different one?
Oh yeah, it doesn't have to be a distribution at all. I mean, like the adversary could make some arbitrary like deterministic choice each day as a function of what's happened in the past. One thing that is important that I forgot to mention is that the adversary picks the label distribution in an arbitrary way, but like in step one. So in particular, the label distribution they pick cannot depend on the prediction. So like the label distribution they pick at round T cannot depend on the prediction at round T. This is important. And what it's going to mean is that the learner can get some mileage here by randomizing. Okay, like one way that will be, we will see as the class goes on, convenient to think about such interactions is as zero-sum games. This is some complicated game in which the learner is interacting with, well, their opponent called the adversary. And we know in zero-sum games that randomization can be really important, right? So like if I'm playing rock, paper, scissors with you, a good strategy would be to randomize uniformly between rock and paper and scissors. A substantially worse strategy would be to always play rock despite the temptation, despite the fact that rock seems like the best one, obviously. And so randomization is really important. And so in general, the algorithms that we're going to derive that are going to have theorems associated with them that say that they can accomplish things in the worst case over adversaries, they're going to randomize. And it's going to be very important that in this model, we have the adversary, although they have lots of power in choosing what happens today as a function of the past, they do not have the power to change what they do today as a function of the realization of our randomness today. Yeah.
So just to clarify on that, so they don't necessarily know PT, but they do know, like if we're doing a deterministic like algorithm, they might be able to like know what PT is based on the past.
Yeah, exactly.
Yeah.
So basically, you can think of the adversary as an arbitrary function from, the adversary at round T, an arbitrary function from like transcripts of like T-1 to distributions over the data domain. So they can do whatever they want as a function of the realized transcript. At day 10, they can choose in any way they want a distribution over, X10 and Y10 as a function of the transcript of what has happened on days 1 through 9. Okay, not on day 10. They don't know the prediction at day 10, but they know everything that's happened previously on days 1 through 9.
So do they know our algorithm, or do they have to infer it from days 1?
they could know our algorithm, because the kinds of guarantees we're going to want to give are that we have algorithms that will make promises against all possible adversaries, including those that are designed specifically to screw up our algorithm. Okay, the one thing our algorithm has, the reason why the game isn't entirely up is exactly this, that the adversary cannot make choices today as a function of what I predict today. Does that make sense? Cool. Other questions? Those are good questions. Okay. Let's think about mean estimation in the start of the batch step. And so maybe the first thing I want to remind you of, we waved our hands at this we waved our hands at this in the first class, but I'll try to wave my hands, slightly less vigorously this time, is that, for like mean estimation, right? Like, we wrote down this idealized goal. We want to just learn the conditional expectation, the label conditional 1x. I just want to remind you of like why that's impossible and why we need to study weaker goals than that. Okay. So let's imagine maybe an infinitely large feature space. And a binary outcome space. Okay, why is the feature space infinitely large? Maybe I'm taking like real valued measurements of different things. And if infinities bother you, it doesn't need to be infinitely large. Just imagine it as large enough so that I'm essentially never going to see exactly the same feature vector twice. Okay, so maybe it's not like literally infinitely large, but like, I've got 100 weather balloons. Each of them is measuring, temperature and barometric pressure and cloud cover and, half a dozen other things to, 10 decimal points of precision or something. Like, I'm never going to see exactly the same set of measurements twice. Okay, that's the important part. And so now let's define two different distributions that have quite different functions f star of x, but will nevertheless be statistically indistinguishable for us if we can only see samples. And so will mean that any kind of goal that corresponds to learning anything that's close to the right f star of x, or even anything that's close to optimal squared error, will be fundamentally impossible unless we make assumptions about the data transferring process. Okay, so here's distribution one. So the distribution on the features is uniform. Feature space, so we're never going to see the same example more than once if we take any reasonable number of samples. And in fact, the conditional label distribution uniform over 0 and 1 for every feature vector. Okay, so like in particular, like under this distribution for all x, f star of x is 1/2. Okay, so this is sort of like the features you were gathering were, entirely irrelevant to the weather prediction problem. Like, God, flips a coin to see whether it's going to rain or not after the features are realized. Okay. I guess the Breyer score here, the best Breyer score you're going to be able to get, Breyer score of the true model, and in particular, the best Breyer score you could get with any prediction method under this distribution is going to be 1/4, because you're always going to be correctly predicting, well, yeah, 1/2. The label will be either 0 or 1, so the square difference is going to be 1/4. Okay, so in this world, it's impossible to learn any predictor that has Breyer score less than 1/4, and f star of x is just 1/2 for every x. But like maybe we're in that world, or maybe we're in this other world, which things are governed by distribution too. And so here, again, we'll see a uniform distribution on features. But now, distribution on labels is just a point mass on either 0 or 1. And so in particular, like ahead of time, God selected which one this was going to be for every x uniformly at random. Okay, so here again, it rains on half the days. The difference is like when did we flip the coins in defining the distribution? In the first case, the feature vector is realized, and then we freshly flip a coin. The probability of rain is 1/2, even conditional on the feature vector. In the second case, in defining the distribution, we flipped a zillion coins up front to determine for every feature vector whether it corresponds deterministically to rain or to not rain. Okay. This is quite a different distribution. So in particular, like the first distribution, the f star of x was equal to 1/2 for all x. In the second case, f star of x, it's different for each x, but like it's always a number that's either 0 or 1. The probability of rain conditional on the features, well, it's either 0% or 100%. Okay, so this is as far as you can get from the first, right? Like these are expectations. So definitionally, f star of x has to be some number between 0 and 1. Up here, it's always 1/2. This is as far away as you can get from that as possible, right? These are at the extremes. This is in the middle. Similarly, the Breyer score here zero. No squared error. You make it, like if you knew the true conditional expectation, you'd be perfect every time. Okay, so these two distributions are about as different as you can get from the point of view of prediction. Okay, here you can get perfect prediction. Here you can't get better than trivial prediction. And in terms of just how far apart these functions are as vectors, here the numbers are all 1/2. Here they're either 0 or 1. And yet, these two distributions are indistinguishable from samples until you have taken enough samples to see the same x twice, right? Because otherwise, otherwise what you're seeing, if you've never seen the same x twice, in either case, is every day a uniformly random feature vector paired with a uniformly random Boolean outcome. The only difference between the two of them is when the coin was flipped. Right? Was it flipped like in defining the distribution, or was it flipped in realizing the sample? But you can't distinguish those two cases until you've seen many samples of the conditional label distribution for the same x. right? Like that's the difference between these two distributions. Here, every time I see the same X, I get the same label. Here I don't. But those, you can't tell the difference between those two things. There's zero statistical distance between the distribution on samples I will get, unless I have substantial likelihood in sampling the same vector X twice, and that'll happen with probability 0 if I've got like real valued features, if the domain is really infinitely large, and with probability essentially 0 if it's really big. Okay.
So what is a point mass?
Oh, it just means like a distribution that puts, like there's like a degenerate case, puts all of its weight on 0. So I just mean like technically a distribution, but it's like deterministically gonna reign today. Good. Does that make sense? Okay, so this is like, in general, the problem with individual probabilities, like because of things like this, there would be ways around this by making strong assumptions, right? Like the way, like a standard thing you might learn in statistics 101 is linear regression. Okay, like linear regression works over big feature spaces. You don't have to see the same example over and over again for linear regression to work. Except like, linear regression works provably at least only when you assume that the data generating process is based on some linear model, right? You've assumed some linear relationship between the features and the labels. That would rule out cases like this, right? So that's one way to go. You can make assumptions and you can sort of rule out cases like this. In this class, we're gonna sort of investigate how far we can get without making some assumptions.
Why is the Breyer score of the first distribution 1/4?
Well, every day you predict, every day the optimal predictor predicts 1/2. That's correct. The expectation of y given x is 1/2 in the first distribution. Okay, so f of x is always 1/2. Y is either 0 or 1.
Oh,
Okay, so the difference is 1/2. And 1/2 squared is 1/4.
Oh, I see. I thought it was uniform, like between like 0 to 1. Like I thought it was continuous.
Well, I mean, that would only have worse Breyer score. Like the optimal model, we haven't quite proven this yet, but like to optimize Breyer score, the best thing you can do is to predict the conditional label expectation. And in this case, the conditional label expectation is always 1/2. So you could try a different model that's, made, say, uniform predictions between 0 and 1. That would only do worse. Good. Other questions? Okay. What do we do with this? Yes, so remember, like, the way I sort of structured the pitch in my slides on the first day was, I said, okay, like, we can start by asking for like really minimal consistency. Like we can't learn the true probabilities. That's impossible because of examples like this. But like we can falsify models that do not produce true probabilities. Like there are some models that do things that are just like inconsistent with measurements that we can take from the data. And so one way we could try to proceed is by asking for our models to pass like increasingly rigorous sanity checks, starting from like really simple ones. And the simplest one we talked about last time was calibration, but I'm going to start even before that. I'm just going to ask for models that do not have statistical bias, okay, which is not going to be like very useful on its own, but it's like a starting point and somewhere we can build off of. What's the like absolute bare minimum we could ask for a model that purports to be predicting the mean, the conditional label mean of a distribution? Let's say that a model and some function mapping features to numbers between 0 and 1, say, has marginal mean error alpha. This really is just going to mean statistical bias alpha, but I'm writing it in this way because I'm going to eventually ask for similar conditions on other distributional properties. If when I look at the difference between the expected prediction of the model, okay, so just, when I look at the average value the model predicts averaged over features drawn from the feature distribution, and I compare that to the actual average of the label drawn from the full distribution, so this is alpha. And if alpha is 0, we'll just say that F satisfies marginal mean consistency. So this is sort of like, this is a very simple sanity check in that although we can't, like learn F star without assumptions, as we've seen, like it is easy to convince yourself that F star satisfies marginal mean consistency, just the order in which you're taking averages, right? Like F star would, for every X, predict the conditional label distribution, the conditional label mean conditional on X, okay, and taking the expectation over X, and then the expectation of Y conditional on X. It's just the same thing as taking the expectation over Y. And so F star, like if we could get our hands on this, like we don't know what F star is, but like it definitely satisfies marginal mean consistency. It doesn't have any statistical bias. And so, if you give me some, I mean, that doesn't help here, like either of these things would have statistical bias, but I could come across a model that you've given me that does have statistical bias, that does have non-trivial marginal mean consistency error. And if it does, I know for sure that the thing you've learned is not F star, and hopefully I can use that information to improve the model. Yeah.
So I understand B, but how do I make sense of the word marginal in the definition?
Good. So I mean, marginal is the opposite of condition. So the thing that we've sort of claimed is impossible without assumptions is to learn F star. And now, what is F star? F star for every X predicts the conditional expectation of Y given X. Right? So it's making predictions that are correct not just on average, but are correct for every X. Here, what the word marginal means is that there's no conditioning. I'm not asking that you get the expectation of Y conditional on X, right? I'm just asking that on average over all of the examples, the average of your predictions equals the average of the outcomes. So I'm trying to average over those things that might be hard to learn. So for example, here, these are quite different models if I look at the individual predictions. Here, F star always predicts 1/2. Here, F star either predicts 0 or 1. But it predicts 0 on half of examples and 1 on half of examples. So both of these models have the expectation of F of X is 1/2. Both of these distributions have that the expectation of Y is 1/2. So without, like this is having no statistical bias is a much easier condition to satisfy than learning F star. I don't need to be able to distinguish between these two distributions to have marginal mean consistency. The only thing I need to be able to do is I need to be able to figure out the average label. And the mean label on the underlying distribution. And like. The thing that's making it hard to learn conditional means here is the fact that basically, I never see more than one sample from the conditional label distribution for every x, right? I never see the same x twice. Okay. The thing I can do from data essentially is take averages over sufficiently large sets of points. Okay. Here, like given, if I want fully conditional guarantees conditional on x, I just never have access to sufficiently large sets of points because I never see the same x more than once. But here, because I'm not conditioning on anything, I can ignore what x is, and if I want to figure out what's the average value of y, I can just average all of the labels in my data set, despite the fact that they have potentially entirely different x's. Does that make sense? Yeah. Cool. And by the way, like that's like, these are sort of polar opposites of one another. Like asking for f star, that's too much to ask for. That's impossible. Asking just for no statistical bias, that's so easy as to be essentially useless. Like, if you don't have to have learned anything other than the mean of the distribution to learn f star. And what we're like, one of the things we're going to be trying to do in this class is find sort of happy middle grounds that are both useful and possible, right? So we're going to try to ask for things that are stronger than this, and that we ask for guarantees that do condition on something. They're not purely marginal, but they don't condition on so much that we don't have any samples to estimate distributional quantities from. Does that make sense? Cool. So yeah, think about learning f star and just learning something with no statistical bias as sort of the two extreme points. This would be super useful, but it's impossible. This is super easy, but not useful. And then, we're gonna try to interpolate and find some middle ground in this class. That makes sense? Cool, good question. Other questions? Yeah.
Wouldn't this make no sense to call it like choice? Because you're using the choice distribution. Not just
Well, except like I never really need the joint distribution. Like this quantity is like defined just on the marginal distribution on x. This quantity is defined just by the marginal distribution on y. So I don't care about basically how x and y are correlated. I'm just asking if the average of your predictions is equal to the average of the averages. Which is why, like the difference between these two distributions is exactly in how x and y are correlated. The marginal distributions on x and y are the same, and that's important for learning f star, but not for statistical bias. Make sense? Cool. Other questions?
If you kind of use the Bayer score to tell if it's distribution 1 or distribution 2.
Well, good. So that's an interesting question. So, and this is again like jumping a little bit ahead. Well, so I'm going to say things that we haven't proven yet, but that we'll one day prove. Okay, so I claimed that the model that minimizes the Bayer score is always f star. Okay, so if I've learned f star and you've learned something that's not f star, we can evaluate the Bayer score of my model. We can evaluate the Bayer score of your model. Mine's going to be lower, and that will serve as very strong statistical evidence that the thing you learned was not f star. Okay, so if you were claiming that if you're claiming that the chance of rain is 1/2 every day, and then all of a sudden, like, I'm the new weatherman in town. You're on channel 5, I'm on channel 6, and I start making perfect predictions every day. I'm like, it's definitely going to rain today. It's definitely not going to rain today. Well, yeah, like if I start doing that, like all of a sudden it's going to be clear that you were not giving, correct predictions because my Bayer score was lower than yours. But that requires, right? So on the one hand, the answer to your question is yes. Like I can falsify an incorrect model by demonstrating another model that has lower Bayer score. On the other hand, to do that, I need to demonstrate another model that has lower Bayer score. And that is you have no information to learn that in this setting if all you're seeing are samples. So you couldn't do it, right? Like these two distributions, the distributions on samples are statistically indistinguishable. So it's true that like if God whispered in the ear of this competing weatherman, hey, like we're in distribution 2, and here's the here's the cheat sheet, you could demonstrate that you did have this knowledge by making the predictions, but there would be no way to learn that model F star just from the data. Does that make sense? Good. But good, like yeah, so that's like a good point though. Like I think a lot of the language I'm going to use in this class is sort of about statistical constraints that we're going to place on models that you can sort of think of as like simple statistical tests aimed at falsifying that the model you have is like F star, right? Like if your model has high marginal consistency error, can't be F star, because F star has 0 marginal consistency error. And we're going to impose other constraints as we go along that are in those lines, like constraints that would be satisfied by F star, but might not be satisfied by other things. Because Breyer score is what's called a proper scoring rule, it elicits the mean, and we'll get to that, but another way to falsify that a model is not F star is just to demonstrate one that has lower squared error. It'll also a falsification. Does that make sense? Cool. Other questions? Okay. Okay, so suppose you tell me, hey, I've got this model F, I think it's like the true conditional label expectations. And then I try to check it. I'm like, all right, I do my due diligence, I trust you, but hey, I'm gonna check if it has any statistical bias. And lo and behold, it does. It's got, high statistical bias, large marginal mean consistency error. Okay, so I know that your model like was not the right one, but maybe it's still useful. Like, can I fix it? Okay, so can I take a model that has high statistical bias, that has large marginal mean consistency error, and like just kind of like tinker with it and remove that statistical bias? And of course, there would be like dumb ways to do that. I could throw away your model entirely and just come up with a constant model that just always predicts the mean. But that's not in the spirit of what I want to do. I want to make use of your model if it is useful. And so I want to do something that's going to not only correct the statistical bias of your model, but will do so by also improving its accuracy, okay, as measured by Breyer score, squared error. Okay, because you could have a model that had statistical bias, but that was still pretty accurate, that had sort of very good Breyer score, had low squared error. And I might have another much less useful model that always predicts the mean of the distribution marginally, that has no statistical bias, but has high error because it's not usefully distinguishing between different features. And I don't want to just throw away a model because it has statistical bias in favor of one that doesn't, if the model that doesn't is much less accurate, it is sort of capturing much less signal. And so the question is, if you hand me a model that has high statistical bias, can I do something very simple? Just like, I don't want to like solve a machine learning training problem or anything. I just want to like futz with it a little bit, remove the statistical bias in a way such that I'm guaranteed to only improve the squared error. Good. Yeah, so what should I do? So suppose you give me some model F, and then I look at it, and I'm like, all right, the average, your model predicts on average, like when I average over all X, that it rains 20% of the time, but like actually it only rains 10% of the time. Like, what should I do to remove the bias?
Play f hat minus f bar plus y bar.
Yeah, good. So I should just, like basically the reason your model has statistical bias, or like one reason, is it might be that you know, like one way you could have statistical bias is you could be correctly differentiating between different kinds of weather events. You could be making correct distinctions between features, like distinctions that really are relevant for the label, but you're just overestimating things everywhere. Like maybe whenever you predict the 10% chance of rain, you know, there's really a 20% chance of rain. When you predict the 20% chance of rain, there's really a 30% chance of rain. Okay, like in that case, I could shift everything down by a constant, by the statistical bias, and recover the perfect model. Of course, that might not be what's going on. Like maybe your model is messed up in some more complicated way. But applying a constant shift like this is nevertheless like a reasonable first thing to try. So suppose you give me some model, right? So let's say fixing bias, some model F. Let's say that delta, I'll write down delta as the bias of the model. So delta is the difference between the expectation y and the expectation of f of x. So if there was no statistical bias, delta would be 0. Otherwise, you know, like the model sort of systematically tends to overestimate or underestimate the label mean. Delta will be some positive or negative quantity. Okay. So like the first thing you might think of to fix statistical bias would just be to shift uniformly all of the predictions that f makes by delta. Right? Cool. So, right, you might like think about fixing the model by defining a new model, f hat of x, just defined to be f of x plus delta. And you might like if I only do this, some of the predictions now might be like more than 100% or like less than 0%. Let's not worry about that for now. Like you could also cap things so that anything that was above 100% was, you know, 100%. Anything that was below 0% was 0%. That'll only be better. But let's just do this for now, and we'll still see improvements. Yeah.
Just like make sure I'm still following. So like the expectations, the distributions are over like our current, what we've seen so far. So like dx and then xy that we've.
I'm just going to define, you know, we'll worry about sort of finite sample issues later. Right now, I just want to define these things over the underlying distribution. So, you know, there's no sample. Let's just pretend that I'm able to figure out what these numbers are. In fact, like, as we'll see shortly, like, because these are such simple statistics, just the expectations marginally over the data, we'll be able to estimate these things quite accurately without too many samples. But for now, let's just assume that like I know what this thing is. It's defined with respect to the distribution. Does that make sense? Yeah. Good. Other questions? Okay. Okay, so one quick observation. Just, you know, like write it down as a lemma to drive it home, but like it hardly deserves the name. You know, this new model f hat of x, no matter what f of x was, this new model f hat of x, which is just defined to be f of x plus delta, satisfies marginal mean consistency. Okay, so like if your objection to f of x was that it had statistical bias, then unsurprisingly, because of how we constructed f hat of x, you know, like that same objection cannot be leveled against f hat of x. F hat of x does not have statistical bias. Great. So like write out a couple lines of algebra. If I look at the expectation of f hat of x, the goal here, the definition of being marginally mean consistent, of not having statistical bias, is that the expectation of f of x should equal the expectation of y. Okay, so just like turning the crank, the expectation of f hat of x definitionally is equal to, well, the expectation of f of x plus the expectation of delta, but delta is a constant, so it's just the expectation of f of x plus delta. And what's delta? Well, it's the difference between the expectation of y and the expectation of f of x. This is just equal to the expectation of f of x plus the expectation of y minus the expectation of f of x. Now the expectations of f of x cancel, and this is just as expected, the expectation of y. Okay, so unsurprisingly, like you have a model, you know, if it has statistical bias, and I just uniformly shift all of its predictions by a constant, the constant that is equal to the marginal statistical bias of the model, I have removed the statistical bias. Okay. You know, okay, like unsurprising, of course, like if all I wanted was a model that was like, that had no statistical bias, I didn't even have to look at f. I could have just, yeah, like why am I getting this thing delta? That's only more complicated than computing the expectation of y. I could have had a model with no statistical bias that ignores x and always just predicts the expectation of y. That would have also had no statistical bias. What, is there anything to prefer this kind of shift? And there is. And it's the fact that, but you know, if I discover a statistical bias of this sort and I shift my predictions, then not only have I removed the statistical bias, but I've strictly improved the Breyer score by an amount that we can exactly characterize in terms of how big the shift was. Okay. And so this is going to be a lemma that sort of is a workhorse for us over the semester. Okay, so fix any distribution D. Okay. Let F any model and let f hat of x be the de-biased model, be the model of x plus delta defined as over here. So the model in which we just subtract off the statistical bias. Then, if I look at the Breyer score of the new model, we know exactly what it's going to be. It's the Breyer score of the old model, the one that had statistical bias, minus delta squared. Okay, so in correcting the bias of a model, I'm guaranteed to get only a more accurate model, one that has lower Breyer score. In fact, how much did the Breyer score decrease? It increased exactly by the square of the statistical bias of the original model. Okay. So this is like one way in which you'd prefer to de-bias a model someone gave you compared to just predicting the mean and having an unbiased model. In that way, this would be more accurate. Okay. Let's prove this. Yeah, and so this was going to be like, even though this is like a simple algebraic lemma, it's worth going through the algebra because this is going to be an important lemma for us. Like in various algorithms, we're going to derive, but like a common framework for them will be that we will identify some subset of the data on which there is statistical bias, right? Like that we'll identify that there's, you know, statistical bias conditional on some event. And we'll try to update the model by sort of shifting it only on that subset. And then we'll find another subset on which there's statistical bias, and we'll try to update the model by shifting it only on that subset. And we'll go around and around. And if these subsets can intersect, you might worry that progress we're making in catching up bias in one part of the model is going to be undone when we patch up bias elsewhere in the model. And maybe we don't make progress. Maybe we're sort of chasing our tail, going in circles forever. But this lemma is going to mean that that can't happen. Every time we correct statistical bias somewhere, if we don't change things elsewhere, we are making sort of monotone progress in the Breyer score. And so this is going to be like sort of a potential function for us that we lean on for a lot of what we do. Okay. So let's just go through the algebra. Okay, so what is this? Let's look at the difference between the squared error of f and the squared error of f. Wanna exactly bound this thing. Well, you can write it out. The expectation of, well, the squared error of f of x minus y squared minus the squared error of f hat of x minus y squared. And we can expand out these quadratics. And we'll get, well, the expectation of f of x squared minus 2f of xy, subtract the cross terms, y squared minus f hat of x squared plus 2 f hat of xy minus y squared. Now already we're starting to get some cancellations, right? Like the y squared here cancels with the y squared there. Okay, so let's take care of those cancellations, and then let's start expanding out other terms. Like we know what f hat is. F hat is just f of x plus delta. Okay, so getting rid of those y squared terms. This is equal to, well, the expectation of f of x squared minus 2f of xy minus, well, f hat of x is f of x plus delta squared. And expanding it out here as well, we have 2 times f of x plus delta fy. Expanding things out once more. F of x squared, 2f of xy, f of x squared minus 2 delta f of x, delta squared plus 2 f of xy, 2 delta y. Okay, and now we start to get a lot of cancellations. F of x squared cancels with minus f of x squared. 2f of xy cancels with minus 2f of xy. And what we're left with is just the expectation of minus 2 delta f of x minus delta squared plus 2 delta y. Okay. Now delta is a constant, right? Delta is just like a number defined by the distribution. Pull that outside. And write that this is equal to 2 delta. Okay, pulling out the terms that have deltas from here and here. 2 delta times the expectation of y minus f of x minus delta squared. Now, what is the expectation of y minus f of x? Delta, right? Expectation of y minus f of x was the definition of delta. So this is just 2 delta squared minus delta squared or delta squared. Okay. Good. So, okay, so let's think about this lemma and what its implications are. Okay, so I sort of foreshadowed how we would use it as sort of a potential function if we try to start iteratively debiasing parts of models, not just whole models. But if you know, I sort of claimed earlier the structural fact about squared error, that it is minimized at the mean. Okay, this lemma is actually a proof of that fact. Suppose the model I give you is just a constant. Right, I'm going to predict like 30% chance of rain always, no matter what. Okay, but suppose that it actually rains only 25% of the time, marginally. Well, then this says that one way I could improve my model is by shifting the model by 5% everywhere. That would give me another constant, 25%. And this lemma is telling me that if I did that, I would have strictly lower squared error. Okay, so an implication of that is that amongst all constant models, the one that minimizes squared error is the one that predicts the mean. Okay, and I could, okay, so that means that so already that's the definition of squared error eliciting the mean. If you minimize squared error over all constant models, you get the mean. But this argument also works not just marginally over the whole distribution, but conditionally on whatever you want. So another implication of that is that f star of x, the model that predicts the true conditional expectation, is the model amongst all models that minimizes squared error. Because if I had some other model, okay, I could look at some x on which it was making an incorrect prediction. I could leave the model untouched elsewhere. Wouldn't change the squared error elsewhere. And I could focus my attention on the conditional label distribution, conditional on x. Okay. And I could apply this shifting argument on that subset of the distribution. And doing so, I would be able to take some other model and reduce its squared error. And I could do this over and over again until I got f star of x. Okay, so an implication of this, this is this lemma that is why squared error is useful. Right? Squared error is going to be minimized at the model that correctly predicts the mean everywhere. And that's true on other scales as well. If I look at constant models that just predict a constant, it's minimized at models that predict the right constant, the mean of the distribution marginally. And as I start looking at models that aren't constant, but are in some more restricted class, the optimal models in that class are going to, we're going to see that we can get monotonic improvements in squared error by looking at essentially subsets of the data distribution on which models have statistical bias and correcting things on that subset. And even when those subsets overlap, right, we're getting to some of what we were talking about in the first lecture, even when there are demographic groups of patients that you care about that are not mutually exclusive, right? You have a gender and a race and a medical history. I can look for statistical bias on each of those, correct them iteratively, and not worry about the fact that maybe I'm just chasing my tail. Maybe I'm ruining progress I made elsewhere with my most recent corrections, because there's this one function, the squared error of the model, that's sort of going to be monotonically decreasing. That's the import of this line. All right, I'll see you guys next week. Yeah, there's quite a, so on the website, we can work, I'm gonna post all these before next week. Lectures. And then there's quite a bit.
But like, I would. Did you estimating that? Maybe yeah, and definitely, I think Ira is definitely, I was working on it, Ira.
Well, you're sure, yeah.
Yeah. Maybe you know better than like.
Okay.
Radium's
nice. That's improved.
I know, right?
You know about. And then. We got This, 505. And then 500. Yeah, and then staff 431.
Yeah, yeah.